Hello, welcome to week 3 of CNST 1731. This week we will be talking about surveys and site plans. Now, we spoke earlier that plot and site plans are going to show the size, the shape, and the location not only of the site but of the building on the lot or the project on the site and its relation to other parts of the site or other buildings. But how do we create these plans? The basis is a survey. There are 3 types of surveys: a property survey, a subsurface survey, and a topographic survey. All are important in print reading. The property survey, otherwise known as a land description or a property description, is a required part of a legal document, what we call the deed, that transfers ownership of a specific parcel from one owner to another. Now, this description positively identifies the land, states its size, its shape, and its precise location in the community. And we create this description with a survey, sometimes called a land survey, sometimes called a property survey. The property survey is described in something called metes and bounds. And this description consists of measurements, otherwise known as metes, and the land which is adjacent to it or which bounds it. The mete is a boundary. It's defined by a distance between 2 points and an orientation or a direction. The bounds is a more general boundary description, such as along a certain water course or the center line of a street. And that direction of the mete is usually defined by a bearing. It's an angle. It's either measured from the north or the south, with east or west as an added designation. For example, here, north 42 degrees 30 minutes west. And the bearings are usually in a northeast quadrant, northwest, southwest, or southeast, measured, notice, from the south or from the north. An important consideration for bearings is that it is never greater than 90 degrees. So north 90 degrees east would be due east. The minute I go into this quadrant, I'm dealing with something that is south some degrees east. Now, the property survey would be a description starting with a point of beginning, and we're told that we're going to go north 14 degrees 20 minutes west, so many feet to a point, thence 77 degrees 42 minutes 10 degrees 10 seconds east, another number of feet to a point, then south 14 degrees 40 minutes 30 seconds west, another distance to a point, and then south 86 degrees 20 minutes west to some feet to the point of beginning, and then it's described in the area, acres or feet, more or less, because they'll never be exact. However, sometimes you need to follow descriptions like that, meets and bounds, to find the point of beginning. So from a nail in the intersection of the center lines of Smith and Jones Road, we're going to go a particular direction, a particular distance, then another direction and distance to some landmark, which will be the point of beginning, and then we follow the same description that we just had, because the point of beginning may need to be surveyed. Now, sometimes the reference point, such as that nail in the intersection, no longer exists, or the reference point has changed. I've seen property descriptions that referenced the branch of an elm tree or a rock, or another property line is used as a reference. You're told to follow the south property line of the Smith property. Well, now you have to find the property description for the Smith residence to know what direction it is. Or the description is old and the handwriting or the terms used are archaic. They're old-fashioned. For example, older descriptions, especially those in the 19th century, the distances are described as chains. And one chain is equal to 66 feet. The chain is broken down into 4 rods of 16.5 feet each, and each rod is broken down into lengths, and 100 lengths equals 1 chain, or 7.92 inches. The chain here is a surveyor's or gunter's chain, and it was developed by an English clergyman and mathematician back in 1620. Sometimes property maps are not drawn properly. Notice here, this did not match up. So these arrows are telling you to move up. This property doesn't exist. This map was drawn improperly. Here's another one. Notice it says here, the map is off. These properties actually match up here, but when this was drawn, it was not drawn properly. Why is a property survey a part of print reading? Well, it tells us the limits of the property that we're working with. We might need that for grading, because in order to get the proper grade, we might be on someone else's property. We want to make sure that our building is not infringing on someone else's property. Codes and setbacks require distances from property lines for buildings to be. Subsurface survey. What is the composition of the underlying soil? What's its strength? Are there any underground utilities that we need to be aware of? And why do we do a subsurface survey for print reading? It will tell us our design approach. Any problems we may encounter during construction because of underground water, perhaps. What construction techniques we are going to use in CNST 2131, Construction Methods and Materials. We'll learn about some construction techniques depending upon the type of soil or how deep we're going to go. And all those techniques will be part of a set of plans. And then finally, there's the topographic survey. This is going to record elevations, locations, information of key features on the site. It gives us a description of the shape of the land. It'll locate any known or existing items such as trees, telephone poles. Are we going to flatten the land or are we going to raise it up? will we be removing or reusing existing features, taking down a tree or making it part of the construction? Why is a topographic survey part of print reading? We need to know what kind of grading we are going to be using. What's the new shape of the land going to be like? Are we filling a hole or are we cutting a hill? Location of features that we have to avoid or incorporate into the drawing. We make use of equipment such as the level, which is simply a telescope that allows us to point a level line, sight a level line. Sometimes surveys will use a transit. It's a type of instrument known as a theodolite, which is an instrument that measures both horizontal and vertical angles. It was developed early in the 19th century, and this telescope could flop over, so you would transit the scope, and that's where it got its name from. This allowed you to easily backsight. In other words, if you're looking in this direction, you could easily look in the opposite direction without having to adjust the instrument. By the middle of the 20th century, the term transit referred to a simpler form of theodolite, and modern day theodolites are a little bit more exotic with a few more features. This one gives you the readings electronically instead of using a vernier. When we level, we use these rods, and these rods will allow us to tell what the height of a location is above the instrument. So how do we make use of these instruments? Anytime we're surveying property to get a topographic map of our land, we start with a known elevation called a benchmark. We set our instrument up and we take what's called a backsight and we read off that rod, and the reading that we find on that rod tells us how high the telescope of the instrument is above the benchmark. That gives us something called the height of instrument. We then take a front sight on any point we want to know the elevation, and reading the rod, we then are able to determine the distance from the height of instrument to that point, and now we know, and by subtraction, we can find the elevation of that point. And we can take as many readings on as many points as we want, as long as we can see it from that one setup of the instrument. If we can't, and we have to move the instrument, then we set up again, take a backsight to a known or calculated elevation, and get a new height of instrument, and continue on for as many points as we need. Now, back in the day, when we used more manual equipment like that, we would have to set up a surveying grid. We would set up 4 points, 100 feet by 100 feet, and we continue setting up 100-foot points, creating this grid. As we would then measure the elevation of each point, we get different readings: 99, 100, 102, 101. You can see that this land is kind of moving around. We would take this information back into the office, plot it, and then estimate and hand draw the 100-foot line. You could see that the 100-foot line might be somewhere between these 2 points, starting here, going through here, and ending here. So that would be the 100-foot line. 101 might be halfway between 100 and 102, and only a third of the way between 100 and 103. So the 101 foot line might look like this. As you can see, 102 would go this way and look like this. Well, that's all well and good, except what if there were a tree right in the way of where this 100-foot grid would end? We would now have to take a site somewhere to the left or to the right or to the left of this point. Now it's no longer at 100 feet, and we would then have to do extra calculations in order to determine what the proper elevation is so we can create these lines. That problem has been solved with the use of electronic instruments. This is what's known as a total station. It is electronic, and when you take a site, instead of using a level rod, you are sighting on a reflector. It will send out an electronic beam, hit the reflector, and come back. And the machine then is able to calculate what the distance is. I know what the height of this instrument is, I know what the height of this reflector is, and it will then compute where this reflector is in relation to the total station, what its elevation is. And so if I have a tree on that 100-foot mark and I move the reflector left or right, the total station will calculate what the difference is in horizontal angle, elevation, and distance, and record it. I take this instrument back to the office, plug it into a computer, download all the information, and then a program like Civil 3D will calculate all those contour lines that I was talking about. This is what we wind up with after we've done all that surveying, and this is what you need to look at in print reading. These shaded or dashed lines indicate that they are an existing contour. This is where the ground is now. These are elevations. This is a major contour. Notice this says 190. This says 185. So this is 180 feet above some reference point. This is 185 feet, and this is 181, 82, 83, 84. So these are the intermediate contours. Because they're shaded, that's what the ground looks like now. The dark or solid lines is what we want the ground to look like. This is what your construction will make it look like. If the lines are widely spaced, it means it is a shallow slope. Over a long horizontal distance, the ground vertically does not change much. However, closely spaced lines mean there's a steep slope. That means in a very short horizontal distance, the vertical elevations change significantly. So remember, closely spaced means steep slope, widely spaced or greater distance between the lines means a shallow slope. And that ends part 1 of week 4. Please now continue with part 2 video.